All right, so what we missed on Friday was largely looking at some of the biochemical applications or bioorganic applications of reduction and oxidation. There's a whole lot that matters a lot when it comes to oxidizing and reducing within our bodies. It's really, really important. But we will, maybe you can save that for biochemistry class one day. Meanwhile, today we're going to focus primarily on the reactions that were covered in the videos for today. Those are the ones that'll be on your quiz, not so much the biochemical stuff, but we'll try to get to as much of the bioorganic reactions as we can at the end of today. So did anybody have any questions on any of this before we jump into the bridge assignments, which covers pretty much all of the reactions for today anyway? All right, so I am going to flash back a little tiny bit and think about kind of not strictly biochemical reactions, but combustion and oxidation and things like that. So what's natural gas? Anybody know what natural gas is? It's one molecule. It's one we've learned about in this class. It's one carbon, all hydrogens.
Methane?
Methane, yeah. So this is methane, and methane is the most reduced form of carbon. So it's carbon with all bonds to hydrogen, no bonds to oxygen. And when we burn methane, which is primarily what we do with natural gas, what do we turn it into? It's the same thing you breathe out. What do we turn carbons into when we burn them or eat them? Nobody knows what you exhale. Everybody take a deep breath.
CO2.
CO2, perfect. Yes, carbon dioxide. And so thinking about this carbon, this is the most oxidized version of carbon that there could be because it's all bonds to oxygen. So this is an example of, and then of course, all of your hydrogens turn into water. But primarily what we're thinking about here is the oxidation and reduction of carbon. So you know from burning natural gas that it gives off a lot of heat. Yes, because this is a higher energy version and carbon dioxide is a very low energy version. So it does turn out that carbon that's reduced is higher energy, carbon that's oxidized is lower energy. This is why fats have higher caloric content than sugars or anything like that, because carbons with more hydrogens attached, like long alkane chains or fats, they have more energy because they're more reduced. And then carbons that are more oxidized would have lower energy. But when you look at the reactions that we're going to go through today, I want you to think about really just how many bonds they have to hydrogens versus how many bonds they have to oxygens. And it's really a trade-off because carbons are always going to make 4 bonds in organic chemistry unless they're charged, but we're going to look at all neutral molecules. What we're doing here, this would be oxidized 4 times because 4 times you've traded off a bond for hydrogen to a bond to oxygen. And so reduction would be to go the other way. So reduction would be if you started off with carbon dioxide. This is largely what plants do, not to this extent, but they start off with taking in carbon that has bonds to oxygen. They start to replace some of those bonds to oxygen with bonds to hydrogen. That would be a reduction or reaction that goes the other way. So instead of thinking about these reactions as, I don't know, 10 or 12 different reactions, thinking them in terms of pots, where we have a bunch of reactions that are reductions with LAH. You have a couple different reactions that are complete reductions, those named reactions, the Wolff, Kishner, and Clemmensen. And then our oxidation reactions, which add more bonds to oxygen. Just to kind of think about them in those 3 pots instead, that'll be really helpful when figuring out kind of what reagent we use for all of them. Because there aren't that many reagents that we use. It's a lot more reactions than we have reagents here since LAH does so many of them. So we're going to focus on that a lot today, is how many bonds to hydrogen versus how many bonds to oxygen and what we're trading off. All right, does that make sense? Any questions on that? You guys might remember from Gen Chem, you did a whole lot of stoichiometry and balancing oxidation states where you might have like a manganese that was a -7 or a 0, and you were putting electrons on both sides and doing all of that balancing. We're not going to worry about any of that. To us in organic, Oxidized means more bonds to oxygen, and reduced means fewer bonds to oxygen. You've reduced your number of bonds to oxygen. All right, so we will stop this. We'll share our screen. And let's go to the bridge. All right, so in this case, what we are looking at are reduction reactions. Specifically, I asked about the ones that use LAH. So all of these result in this carbon right here being reduced. And the way that we know that is these reduction reactions with LAH always end up with one bond to oxygen or nitrogen. And because that's kind of our leftover bond, and they will add more bonds to hydrogen. So again, oxidation adds more bonds to oxygen. Reduction will add more bonds to hydrogen. So in order to make these from reagents, and this is pretty open-ended, but you guys hopefully had your notes in front of you when you did this. So Miguel, tell me what I could start with and reduce it to turn it into carbon with one bond to oxygen and then a couple of hydrogens.
What I put was a benzene ring with a ketone.
Yeah, so a benzene ring with a ketone would change your number of carbons, but just an aldehyde here, like acetyl bondo.
I put a C double bond with another carbon, so I guess that's wrong.
So in this case, with LAH, we're never adding or removing carbons. So we have to start off with the same number of carbons that we end off with. So since this carbon here has two H's, it must have only started off with one. So you could have done a carbon dioxide, sorry, an aldehyde there, like this one, or a carboxylic acid here, but you'd have to keep the same number of carbons. So for all of these, make sure that you guys have the same number of carbon in your starting materials and your products. So here we are going from a carbon with two bonds to oxygen and one bond to hydrogen, and we're turning it into a carbon with two bonds to hydrogen and one bond to oxygen. So we've removed a bond to oxygen, added a bond to hydrogen, and therefore this is a reduction reaction. And what reagent did you add?
Oh, is it still me? Sorry.
Yeah.
The reagent functional group, you mean?
Well, so the thing that you would add then would be LAH followed by. In this case, the second thing is what protonates that O minus. So you could just add an H plus, or you could just do water. So when you are reducing with LAH, it's always going to be these two things in order. Step one, LAH. Step two, H plus and water. And the way to know that this is the reagent set you're using is if you're starting with a carbon that has more bonds to oxygen or nitrogen and ends up with a carbon that has only one bond to oxygen or nitrogen. That's why the reagent for all of these is going to be LAH. And that was the question here, the reactions that use LAH. They start off with more bonds to oxygen or nitrogen. They're removing bonds to oxygen or nitrogen, replacing them with more bonds to hydrogen. Does that make more sense?
Yeah, I got it.
Okay. All right, so Olivia, tell me, there's a lot of different ways to make amines through reduction. Tell me one thing we could start with, one functional group we could start with.
So I use the same amount of carbon, so the benzene ring with one carbon chunk, and then at the end of that I used a halogen, and I used a BR.
Okay, so we don't want to be worrying about multiple functional groups at the same time. We wouldn't want to have halogens there. We would want to instead focus on, in the video, there are a bunch of different functional groups we could start with that you can reduce down to amines. Did you catch any of those?
A nitro, an NO2?
Yeah, a nitro. So a nitro works. So I'm going to put that a little bit off to the side because nitro doesn't actually use LAH, but that's okay. So here's the deal with, I'm glad you brought it up because nitro is the only reaction that actually doesn't fit into this bridge anywhere. So a nitro can absolutely be reduced down to an amine. And we would do this. LAH does not actually work for a nitro. Instead, there's a couple different things you can do. You can use zinc with some acid, or you can use hydrogen and palladium, which was a lot like what we used when we started off with like an alkene and turned it into an alkane, which is actually a reduction reaction that adds more hydrogens. More often than not, so nitro is new to us, right? We haven't seen nitros before today. Nitro is not something that we have a lot of good ways of attaching to alkanes. We do have good ways of attaching them to benzene rings. So we'll really start seeing nitros this Friday. So this is kind of, this is an important reaction for us. We haven't really gotten to nitros yet. We'll really worry more about nitros starting on Friday. So that's why I wanted to put it in here, because it is the same kind of thing. You're removing bonds to oxygen and adding bonds to hydrogen, but that's a one that we'll get to a little bit more starting on Friday. But these are indeed reductions, but they, because they remove bonds to oxygen, add bonds to hydrogen, but they're actually not reducing a carbon. They are reducing a nitrogen itself. All right, but we got one. So Kylie, can you tell me anything, any functional groups that we can reduce down to amines?
So I did like what Olivia was saying with the BR, like the benzene ring with the BR coming off.
Okay, so that's
And-
not gonna work with multiple functional groups. But did you get anything else for the rest of these?
I
What
got
other
the
function?
one that you just drew up there.
Okay.
And then I had a benzene ring with a ketone and a NH2.
Okay, so good, we're on to something. A C double bond O with an NH2 is not a ketone. What is the name of this functional group here? Anybody remember?
Shoot.
Is it an amide?
Amide, yes. So what we do here, this is an amide, and an amide is one of three functional groups that we can reduce down to an amine. So what it does, this is the only carbon that changes, this one right here, is that we remove two bonds to oxygen, replace them with bonds to hydrogen. And the reagent that we use for this is the same as above. It's LAH followed by either acid or water. This one is a little bit different from the rest in that we're actually going to kick that oxygen off completely, but we still end up with one bond to nitrogen. So we are replacing it with two hydrogens, and those two bonds to oxygen are replaced with two bonds to hydrogen. So it has been reduced and we end up with nitrogen attached. All right, Timothy, besides an amide, what else can we reduce down to an amine?
Could you do an amine that's double bonded? Is that something?
That is something. We made that last week. Remember what that's called? It's a C double bond N.
Triple bond is nitrile. Isn't that a
This is an imine. This is one that we didn't name at the beginning of the semester, but this was one that was in the video as well. This is a really important one. And it's actually pretty straightforward. It's very similar to the reaction of an aldehyde. LAH is going to provide an H minus. So LAH today does the same thing that LAH has done every time we've seen it. We basically cross it out and mentally replace it with an H minus, which is a hydrogen nucleophile. So hydrogen nucleophile attacks the electrophile, kicks electrons up, and that would turn your C double bond O into a C single bond O and add in a hydrogen. That's the reduction step right here, there. Reducing an amide is more complicated. It's multiple steps, but the first one, as you can imagine, would involve this as well. With the imine, it's just as simple as the very first step up here. You would have an H minus attach or attack the carbon in the C double bond N, kick electrons towards the N. Because nitrogen's more electronegative than carbon, it's pulling electrons away. So attacking that carbon, kicking electrons up, pretty simple and straightforward. You would add a new hydrogen at the carbon. So your carbon has been reduced. You've added more bonds to hydrogen. And now you have, instead of two bonds to nitrogen, we end up with only one bond to nitrogen. The second step would add in the hydrogen that would go on right here. All right, Timothy, you mentioned in passing the other answer to this question. Yesenia, do you know what the other thing is that we can reduce? It's another common functional group we can reduce down to an amine.
A nitrile?
Perfect. Yes. So a C triple bond N. This one would be multiple steps as well because you're reducing twice. You end up losing 2 bonds to nitrogen and add 2 bonds to hydrogen. But once again, the mechanism would start off the same way. You have an H minus, you attack that carbon, kick electrons towards the nitrogen. And we end up with a carbon that in this case has 0 bonds to hydrogen. In this case now has 2 bonds to hydrogen. So all of these are really good to put into your functional group interconversion flow charts. They would all look like this. We've got here, this is an aldehyde, but it could be a ketone. And we can reduce it over to an alcohol. It uses LAH followed by water or followed by acid, and it doesn't add or remove any carbons. The rest of these are all going to turn into the same thing, which is an amine. Amines are functional groups we learned about really early in the semester, but these are really the first reactions that we've had where we actually make them reliably. So the first one is an amide. The second one here is an imine, which we just learned how to make last week. And the third one is a nitrile, which we had as a product from the beginning of the semester for SN2. And all of these can be turned into amines with LAH. It's the same reagent. It reduces all of them down to amines. So all that these reactions do is they add more bonds to hydrogen and remove bonds to either oxygens or nitrogens. All right, so please don't try to do any of this with halogens or anything like that. I understand that we can kick off a halogen or replace it with a hydrogen, but really that only works if the halogen's your only thing in the molecule. Much broader picture, we are turning functional groups that we know about already into functional groups that we know about already as well. But LAH is the way that we do this. So this one up here at the top, this is not a new reaction. We did this back in outcome 5, turning a carbonyl into an amine, or sorry, an alcohol. But the rest of these are new to us. And we are turning them all into amines. Any questions on any of that? Does that make more sense, maybe what I was asking?
So for the nitrile, I think everybody in the video had something using alkyl halide to turn it into a nitrile and then into a amine.
Right,
What do
okay.
you do with the benzene ring? Is there something to do with the double bonds in it?
Yeah, I'll check everybody's flow charts, but unfortunately you can't actually make this here because if you had a halogen like a bromine there and you added nitrile or cyanide, you can't do an SN2 reaction when you have a ring. You can't do an SN2 reaction when you have a carbon with a double bond. So it actually doesn't work to make this, at least in this specific case. We would just have to start with this. There are other ways to make this we'll get to next week. But this is where we'd have to go. So I'll check through everybody's bridge assignments. I haven't had the ability to do so yet, but I'm a little bit behind. I'll get caught up on those, but this is, these are the functional groups that you should be looking at as starting materials for right now. Sorry, was that, go ahead with your question, Timothy. I think I cut you off.
No, that was it, sir.
Okay. All right, so these reactions down here are a little bit different. These reactions all start with, well, let me go back to your question. Yes, there are absolutely ways to make nitriles and then you can reduce them. So we could do this in multiple steps. Not in this case, but in most cases. Likewise, we know how to make imines. You actually make imines from aldehydes or ketones. So we could go back one step to do this thing as well. We haven't ever talked about how to make amides. I guess we have from acid chlorides or esters. We can make amides as well, and then you can convert them over. So sometimes these are part of multi-step reactions, but for today and for the quiz on Wednesday, all I'm really worried about you guys focusing on is this step. An important side note, all of these reactions are and must involve LAH as step 1 and your acid or water as step 2. So I will warn you that I will be grading you as wrong if you say that you toss them all in together, because LAH is an H minus. And if you toss in an H minus and an H plus, you have to add them stepwise. So little 1 and little 2. If you don't say little 1 and little 2, you're saying that you're tossing them in together. And if H minus and H plus get together at the same time, they just make hydrogen gas, which is H2. And then basically what will happen is that just bubbles out of your reaction and catches on fire. And nothing will happen in your pot. You'll just end up exploding the entire thing. So this cannot be LAH water. It has to be step 1, this, step 2, that. You have to add them in separate steps or else they just won't work.
Hello, Dr. Green.
Hello.
This is Sydney.
Hi, Sydney.
I was just wanting to ask to clarify, it is / not comma, because it's one or the other. It's not both for the second step.
Gotcha. So I meant when I said / I meant this or that, and that is fine. For a step 2, you could say H plus, you could say H3O plus, you could say H2O. Frankly, you could say like methanol or something like that. That second step, the whole purpose of it is to turn an O minus into an OH or an N minus into an NH, and it's really easy to do. Remember in lab when we were doing the camphor reduction and you just dumped all that stuff in water? Ice water? That's all it would take to protonate an O minus and turn it into an OH. So it doesn't take anything fancy. So whatever you guys write for step 2 is absolutely fine with me. Frankly, if you just put LAH, that would be fine with me as well, but please do not say this. Because if you say LAH and acid, what you're saying, even if you put one on the top of the arrow and one at the bottom of the arrow, what you're saying is you're tossing an H minus and an H plus together. They're basically just going to explode. So it's important to keep track, especially in this reaction, that it's a step 1 and a step 2 that you're doing them separately. But yeah, what you put down here isn't, it's important that we would add it, but it could be an H plus, it could be a water, it could be a whatever. Does that make sense?
Thank you for clarifying.
You are welcome, Sydney. Sydney, since you're on the phone, would you talk us through what's going to happen here, at least in terms of the product? So these are different reduction reactions in that they are complete reductions. So what would this, we call this the Wolff-Kishner reaction. What would it do to the starting material?
So I put that the starting material is a ketone.
Yep.
And what happens is it's breaking, so it's attacking the electrophilic carbon.
Perfect.
And it's breaking that double bond O, and it's making 2 H bonds.
Perfect.
Hydrogen bond.
Exactly right. So this is a
plus-
reduction.
Gas.
Yes. So as in most of the cases in this class, you are absolutely correct. You would get some water, you would get some nitrogen gas, and that's kind of what forces this thing forward. But what I'm looking for and what we're mostly worried about here is what happens to that carbon chunk. And so your carbon chunk here that was 6 carbons with a ketone is turning into 6 carbons of just an alkane. It differs significantly from the above reductions because whenever you use LAH, notice that you end up with 1 bond to oxygen or 1 bond to nitrogen or 1 bond to nitrogen or 1 bond to nitrogen. But you always have that heteroatom, the oxygen or the nitrogen, hanging on by 1 bond at the end. It doesn't kick it off completely. These reactions are different in that they kick that oxygen off completely. It's all the way gone. You don't stop at 1 bond to oxygen, you end up with 0 bonds to oxygen. So this, you're absolutely right on this. The carbon that gets changed is the one that's in the double bond O here. It's the functional group, it's the one with function. And it ends up with 2 bonds to hydrogen, replacing 2 bonds to oxygen. So that's exactly right. Ellie, how's it going?
I'm good. How are you?
I am better today, thanks. So when we started with this ketone, which is a cyclohexanone, We add the Clemenson reduction, which is another way to do the same thing. What do we end up with?
Cyclohexane.
Perfect. So that one carbon gets reduced twice. We replace two bonds to started with two bonds to oxygen. We end up with two bonds to hydrogen, and it goes from a ketone to an alkane, and you're done. All right, that's it. Perfect. Good. So these are also functional group interconversions in that they aren't adding or removing carbons. They are starting with one functional group that we know already and turning it into a new functional group that, or not a new functional group, but a functional group we knew about already as well. But basically, this is just a new arrow on your functional group interconversion flowchart. So these are our two really big forms or two buckets of reductions. LAH, as I mentioned, always ends up with one bond to oxygen or nitrogen left over. And these Wolff-Kishner and Clemenson reduction end up with no bonds to oxygen or nitrogen left over, just complete reduction all the way down to an alkane. All right, so the first one, we had 4 different reactions that all had the same reagent. And in this case, we have one reaction with 2 different reagents. And realistically, we have lots of different reagents that can carry out the same reactions. And part of the reason for that is that many reagents will muck with other functional groups. And if you start doing organic chemistry with lots and lots of functional groups and bigger molecules, you want to have a reagent that only affects the one part that you want to impact. And there aren't usually just one perfect reagent that will only focus in on one thing. That's why we talked about protecting groups a little bit last week, that those are important. But another thing is that having a variety of different reagents that can do the same thing is good, especially when you have other functional groups. Sometimes one set of reagents won't impact like the alkene, and other sets of reagents would. So you got to be careful as to which one you choose. So which of those 2 did you guys choose to do this reaction here? Just leave this open to anybody.
The basic one.
Basic one, yes. So if I started off and I did the acidic one, which was this Clemenson reduction with zinc, mercury, amalgam, and some hydrochloric acid, it would absolutely reduce this carbonyl down to an alkane, which is what we're after. But what would the HCl do to your alkene? Anybody remember that reaction? No, it's okay. It's been a while. But you guys chose correctly. So yeah, an HCl will react with an alkene, and it would end up doing a Markov-Nakov addition of H and Cl. So this reagent set would do what we wanted to this ketone here. But in addition, it would also react with the alkene. So if we don't want to react with the alkene, we would have to use this guy. This was the most challenging question, I think, on this bridge assignment. When we use NH2, this Wolff-Kishner reduction, what's going to happen is it will reduce this carbonyl, but bases don't react with alkenes, amines don't react with alkenes, heat doesn't react with alkenes. So the alkene would stay put, and all that you would do is reduce down this carbonyl down to an alkane. There are going to be conditions where bases would mess up other functional groups. And in that case, the Clemenson reduction would be the best thing to use. But in this case, this would be the best reagent set. This would do other things to other parts of the molecule. All right, good job, Ellie. So let's move on down here. So if that's bucket 1 and bucket 2 of reduction reactions, this is all of your oxidation reactions all rolled in together. And really what they're all doing is they're all starting off with alcohols and looking at how we can add more bonds to oxygen. And just like the reduction reactions, removed bonds to oxygen or nitrogen and replace them with bonds to hydrogen, oxidation reactions will add bonds to oxygen, but remove bonds to hydrogen. So you need to have bonds to hydrogen in order to do oxidations. You just won't be able to otherwise. So looking at all of these, this carbon has its 4 bonds already. It doesn't have any bonds to hydrogen. This carbon has its 4 bonds already. It doesn't have any bonds to hydrogen. This carbon has 3 bonds shown, so it must have 1 bond to hydrogen. And this is obviously the same molecule. These carbons here only have 2 bonds shown, so they must have 2 bonds to hydrogen as well. So the carbon that we are oxidizing, or the carbon that we're reducing, is always the carbon that's part of our functional group. It's the one that's attached to an oxygen or a nitrogen or something like that. And so that's why this is the carbon I've keyed in on. This is the carbon to which the OH is attached. This is the carbon to which the OH is attached. And down here, here's your carbon to which the OH is attached. So that's always what I would look at first, is whichever carbon has the functional group, that's the one that you're going to oxidize or reduce. All right. So since we have to trade off hydrogens for oxygens when we're doing oxidation, how many times could we oxidize this carbon? We got 2 hydrogens.
2.
Perfect. Gotta keep going. You got 1 bond to hydrogen, how many times could you oxidize?
One.
We're all nodding and pointing up, holding up 1 finger. Once. All right, what about this carbon down here? How many times could you oxidize that carbon? If you don't have any bonds to hydrogen, you can never oxidize it. So 0 times would be correct. So these are going to be really easy questions to answer because you can't oxidize them. All right, so let's move up to the top here. These first 2 questions are really the only ones that have any difference between the 2. And that is the fact that if you have 2 hydrogens that you could reduce, that you could oxidize, you could either oxidize 1 of them or 2 of them. If you only have 1 hydrogen to oxidize, you can either oxidize it or not at all. But this is the only time there's any sense of nuance here. So with chromic acid, we'll go through the list again. Miguel, when you add chromic acid, how many times does it oxidize?
Chromic acid would oxidize it twice.
Yep. So chromic acid will oxidize as many times as possible. And so if you've got 2 hydrogens in your functional group or on your functional group carbon, you'll oxidize it twice, and that's perfect. So we would trade off 2 bonds for hydrogen, 2 bonds to oxygen. And what functional group have we made here?
Carboxylic acid.
Perfect. So chromic acid will oxidize a primary alcohol, or an alcohol with 1 carbon and 2 hydrogens, all the way to a carboxylic acid. Olivia, what about PCC?
It is going to oxidize twice.
Once.
Once.
Once. Perfect. And so PCC will always, it doesn't always oxidize once, because if you added PCC twice, we would make the logical thing that it would go twice. But it doesn't do that. It only oxidizes until you stop at a ketone or an aldehyde. And it won't go all the way to a carboxylic acid. So you're right. In this case, what it will do, chromic acid oxidized twice. It removed both of those hydrogens and replaced them with oxygen. In this case, PCC will oxidize once. So it'll remove 1 of those hydrogens. And you don't really add another oxygen. You just add another bond to your oxygen that you had already. So leaving the oxygen in the same place, it's the same oxygen, but instead of a C single bond O with 2 H's, you have a C double bond O with 1 H. So this is the only time that PCC really matters, is that you get different products with chromic acid versus PCC, because PCC will oxidize to an aldehyde or a ketone. Chromic acid goes all the way. Good. All right, Kylie, if we are starting with a secondary alcohol, so we've talked about primary, secondary, and tertiary before, just means how many carbons are attached. But we want to really focus on the number of hydrogens attached. If you only have 1 hydrogen attached and you add chromic acid, how many times do you oxidize?
So only once, right?
Right. So we would remove our hydrogen and replace it with what?
A double bond to oxygen.
Exactly. We'll just add one more bond to that oxygen. And so this would end up turning this molecule into a ketone. So once again, all of these are functional group interconversions that you can add. This is, excuse me, how we can turn an alcohol into a ketone. This is how to turn an alcohol into an aldehyde and an alcohol into a carboxylic acid. These are all oxidations because we're removing hydrogens and adding oxygens. Pretty much all of these reactions just go backwards if you add LEH. All right, who's next? Ellie, PCC and chromic acid. If I start with one hydrogen, how many times am I going to oxidize?
Once.
Perfect. So you're going to end up with the exact same thing that Kylie made a second ago. It turns out that when you only have one hydrogen, chromic acid and PCC do the same thing. They're going to oxidize it and stop at a ketone because all the way oxidized is a ketone in this case, and oxidized once is a ketone in this case. So it's the same either way. Timothy, what are we going to get from these reactions?
You're going to get no oxidation because there's no hydrogens.
Perfect. So we end up with exactly what we started with.
Bless you.
Thank you. So there'd just be no reaction here. You would end up with hopefully recovering the exact same thing that you started off with. Because that carbon, the one that has the alcohol, doesn't have any hydrogens for you to oxidize. So that would be the end. All right, any questions on these reactions? So your quiz will look a lot more like this page and this question right here. I wanted you guys to think about these backwards a little bit, but instead your questions on a quiz would look way more like, if you start with this imine and you add LEH, what are you going to get? So you're really going to have, as has become the trend in this class, two styles of questions. One is starting material plus reagent. The other one would be, what would be the reagent that you would use? So let's practice some of that type of question. So we're a little bit prepared for that. All right, so if we were to start off with, let's say this molecule right here, and we wanted to turn it into that product, what reagent would we use? And you're welcome to think about it or say it out loud, but here's how I would approach this type of question. Look for the carbon that's changing. And so the carbon that's changing is this one right here, because it's starting off with a C double bond O and a nitrogen, and it's ending up without the C double bond O. But it's not that the C double bond O is just gone, replaced with nothing, much is the case in the kind of the trickiness of line angle structures. What we've replaced it with is two bonds to hydrogen. So Yesenia, when you are removing oxygen and adding hydrogens, is that oxidation or reduction?
Reduction.
Perfect. So oxidation, this is the easiest way to remember it. Oxidation is when you add oxygens. And reduction is the other thing. So here we're removing oxygens, which is the other thing, which is reduction. And so when it comes to reduction, you really only have two sets of possibilities. If you end up with one bond to nitrogen or one bond to oxygen, the answer is pretty much always LAH. And if you end up with just an alkane, that's when we had those kind of complicated reagent sets. So in this case, what's your reagent that you would use? Notice that you still have one bond left over to nitrogen, which is a hallmark of one of those first set, or first bucket reactions. They all use the same reagent. Anybody know?
LAH.
LAH, right. So again, step one, and then step two is I'm going to add some water. And so that is a way to do this reaction. All right, I'm going to change things up very slightly here. And so once again, focus on the carbon that has changed. Here is your carbon that started off in a functional group and it ended up with just hydrogens. So Sydney, has this carbon been oxidized or reduced?
Reduced.
Correct. And Sydney, this is reduction all the way. There are no leftover single bond oxygens or single bond nitrogens. So tell me one way to do this reaction.
I'm gonna go the acidic way.
Okay.
Zinc and mercury.
Zinc and mercury. Great. With some acid of some type. Let's do some HCl. Perfect. That is the Clemmensen reduction. You do not need to remember Clemmensen's name, but zinc and mercury with HCl is perfectly fine. It is also absolutely fine if you guys wanted to go the base way and do that NH2 in step 1, followed by step 2 with some base and some heat. Either of those would be perfectly fine in this case because there are no other functional groups, so both reagent sets would work perfectly. All right, let's look at some oxidations. So if I was to start with this thing, wanted to turn it into that thing. Timothy, what would I use?
I gotta press spacebar. To go from an alcohol to an aldehyde.
So
You'd have to-
go ahead.
No, you're fine.
So you guys can think about these as 12 different sets, but let's at least steer ourselves into the right bucket here. This is the carbon that is being changed, right? And it's starting off with 2 bonds to hydrogen. It's ending up with 1 bond to hydrogen, starting off with 1 bond to oxygen, ending up with 2 bonds to oxygen. So is it oxidation or reduction?
This would be oxidation.
Yes. And are you oxidizing it all the way?
No.
No. Good. Does that make sense? So kind of thinking about it that way, instead of trying to memorize everything. I know that there's some memorization with this, of course, but a part of the way of figuring this out is not trying to think of everything as just one functional group into another functional group. That works well if you're just reading it off like the reagent off a chart. If you're having to remember it, the chromic acid is the way that we oxidize all the way. What's the other way of oxidizing?
The PCC thing?
Perfect. And you don't have to tell me the solvent. This is fine, PCC, that's it. Okay. What if I want to do this reaction the other way around? So Miguel, what if I want to go this way? Would that be oxidation or reduction?
Ellie says reduce.
Ellie says reduce. Ellie is correct. Ask Ellie if it is all the way reduced down to an alkane or if you still have 1 bond left over to an oxygen.
Sorry, my microphone was off. I didn't realize.
No, you're fine. I'll get you next time, Miguel.
Oh, okay. You have 1 bond.
Right. So what's the reagent?
LAH.
Perfect. Step 1, LAH. Step 2, some water or some acid, whatever. All right. Miguel, are you ready?
I'm ready.
Okay, so you guys actually, and I am sorry about this. You guys have 2 new quizzes on Wednesday. Hopefully neither one will be tremendously overwhelming. In case you didn't read or missed all of this, you won't have any quiz at a specific time. Just all of your quizzes will be from 8 a.m. to 8 p.m. You can take them all whenever you want to. Hopefully that'll make it a little less rushed. It's so you won't have to be, there is no like 30-minute gap for one quiz this week. They're just all going to be open all day. But one of these, this is a reaction from last week. So if you don't remember, it's okay. But if I wanted to start off with that guy and turn it into an imine, you remember what I would do to swap off a double bond O for a double bond N, Miguel? If not, it's okay.
Would it be the NH2 with whatever that substituent is?
Yep, that's it. Perfect. So you just add your nitrogen with whatever you're toting along with it. You just add this whole thing. The second thing, you do need to add a little bit of acid. From my personal experience, it'll still work, but a little bit of acid makes it go a lot faster. And you will swap off this oxygen, the double bond O, for a double bond N. So this is not an oxidation reaction, and it is not a reduction reaction. You're just swapping 2 bonds for oxygen into 2 bonds to nitrogen. But yeah, so that's one of our reactions. And it turns out that this is going to be a really, really good way, probably the most common way to make an amine, is that we can turn a double bond O into a double bond N, and then we can turn a double bond N into a single bond N, which is what an amine is. And so in this reaction, which I'm drawing now, kind of this second step, here is the carbon that has changed. It has gone from 1 hydrogen and 2 nitrogen bonds to 2 hydrogen and 1 nitrogen bond. So Kylie, what is the reaction? Oh, sorry, let me back it up. Is this an oxidation or a reduction?
Would it be a reduction?
It would, yes, perfect, because you're adding bonds to hydrogen. And so what's the reducing reagent that leaves you 1 leftover bond to nitrogen?
Would it be the LAH?
It would, perfect. The more you practice this, more you'll find that LAH is the answer to most of your reduction questions, because LAH is the king reducer. It's really, really great at this. So all of these kind of go hand in hand. Notice that my double bond O can turn into a single bond O using LAH. My double bond N can turn into a single bond N using LAH. So those are kind of pretty parallel reactions. We don't have a way to undo this one. If we oxidize, usually we're just adding bonds to oxygen. So we don't really have a good way to oxidize this C single bond N into a C double bond N. We do have a good way to do this one backwards. And this is last week reaction stuff as well. Yesenia, do you remember how to turn a C double bond N into a C double bond O? It's the backwards version of this reaction. So don't look it up, think about it. If I wanted to add this chunk, I added this chunk. And if I want to take this chunk off and add just that little chunk, just oxygen, I need to add some oxygen. What would be the simplest source of oxygen? Maybe lugging a couple hydrogens with it.
H2O.
Perfect. And that's it. So with H2O, you add on the oxygen. And with this nitrogen and all that junk, that's what you're adding on. This is how we go this way. That's how we go that way. So there were not a lot of reactions on last week's quiz. There were really 3 reactions in the backwards versions, and this is one of them with its backwards version. All right. Any last second questions? I've got one more, we've got a couple more things I want to ask you on here. This all seem good, okay? All right, so let's look at, might not have any time to get to biochemistry today, but that's okay. What if I were to start with this alcohol right here, and I wanted to oxidize it to carboxylic acid? What would I use? Yeah, that's the right number. Is this an oxidation or a reduction? Olivia, what do you think? Oop, I lost Olivia. Oh, and are you here? Do you have a mic?
Yes.
Okay. Sorry, I didn't see you there. I haven't called on you earlier. Are we oxidizing or reducing this carbon here?
Oxidizing?
Yes. And am I oxidizing this all the way or partially?
All the way?
Yes. So what is the reagent that I should use? PCC.
Would it
Go ahead.
would it be the PCC?
No, the PCC is the way that I oxidize only once if I've got two hydrogens to oxidize. So
Okay,
let's-
so would it be the CrO3?
Yep, perfect.
Okay.
So chromic acid and some, chromate and some acid, which makes chromic acid. Perfect. All right. And on the flip side, so if I started with this thing and added PCC, this one would be the one that oxidizes only once. And so this one would oxidize and leave one hydrogen left over, a double bond. So that would be the difference. This is the only time that we have a difference between these two reagents. All right. Any questions? How do you guys feel about this? We're going to practice it. Find that it gets pretty repetitive because while this was quite a few reactions, there's not that many reagents. They get used pretty regularly for different purposes. All right, I do want to show you in my last 7 minutes here, we're going to go over to the bridge assignment from last Friday that we didn't have a whole class on it, but I do want to show you one little thing. And that is that. So if you guys turned this bridge in assignment, this was the one where I asked you to draw some biomolecules. We didn't have class on Friday and you guys know that. So some people turned it in, some people didn't. It's fine either way. But whether or not you did, I wanted to show you something really neat about biochemistry and why all of this oxidation and reduction matters a whole lot. So these molecules right here, this glyceraldehyde 3-phosphate, I expected that you guys had to look these up, which is absolutely fine. So this is an aldehyde though. And I'm not going to spend a lot of time on this. This has an O and a phosphate. I'll write that part small because it doesn't matter. These are the kind of steps 6, 7, and 8 of glycolysis, which is a 10-step process. You do not have to write any of this down. I'd rather you just try to follow along a little bit. This one has 2 phosphates. And then the one on the right here, a glycerate as opposed to a glyceraldehyde, the first one. And 8 is a carboxylate, which looks like this. So while I could spend a whole lot of time talking about this little 2-step process, what I really want to key in on is this chunk right here. Particularly overall what has happened from beginning to end. So we started off with an aldehyde and we end up with a carboxylate. So overall, going from here to there, and notice that nothing changed in the rest of this molecule. So overall, is this an oxidation or a reduction?
The oxidation,
Yeah, how do you know?
because it replaces the O with the H with the O.
Yep. And so it's only oxidizing one time. You're going from a hydrogen to an oxygen, just one time. So this might seem incredibly simple, right? I mean, it is simple. It's all you're doing is turning one hydrogen into an oxygen. But in this process, this is where the vast majority of the energy in glycolysis comes from. So we know about glycolysis. You guys have had to, I'm sure, in many of your biology classes, learn about glycolysis and how many ATPs and NADHs you get out of it. And all of that is true, but the first half of glycolysis actually requires an energy input. You don't get any energy out of it. In the second half, you get a lot of energy here, which is the beginning of the second half, 6 and 7. Then you get a little bit of energy at the end. But this is where the vast majority of your energy in glycolysis comes from. And it comes from oxidizing one time, just turning one hydrogen into an oxygen. In fact, in this step right here, we end up adding in that phosphate. All you do is add in a phosphate here. It's basically a substitution. You add in this phosphate, doop, doop. You're kicking off a hydrogen. You basically get out an H minus. And in this step, you're taking off a PO3. So that's ADP, which is adenosine diphosphate. And it's just gonna sneak in here and grab that phosphate, and it becomes ATP. And so there's two main energy molecules in our body. One of them is ATP, and you don't get ATP out of nowhere. You get ATP by starting with ADP and adding a PO3 to it. And so it always seemed like a miracle to me when I was looking at learning about these pathways. At first, it just looked like all of a sudden ATP shot out of a reaction, and good news, all of a sudden you've got energy. But really, it's about your recharging batteries. So think of really this as one of the two rechargeable energy sources in our bodies, where you go from ADP to ATP by sticking a phosphate on it. And it has to come from a source where it's pretty high energy in order for it to go over to ATP in the first place. But this is where you get one of your ATPs from. You just have ADP scoop off a PO3, and there you go. But this is actually the most meaningful energy change here in all of glycolysis. This is where we get most of our energy, is just from this one H minus coming off. And this is one thing that you guys have learned about many times before, I'm sure, but I'm gonna scroll up a little bit here. NADH is the other molecule that's high energy in our bodies that we use. NADH, we turn into NAD+. You guys, I'm sure, have heard about this a lot, but it cannot be overstated how important ATP and NADH are for living systems. This is just basically how we run energy around our bodies. So what's the difference between NADH and NAD+? So molecule-wise, what are we missing in the product?
Hydrogen.
Yep. Charge-wise, what are we missing in the product? So it's neutral to start with, so it needs to be neutral overall to end with. You got a plus, what must you have? It's the thing that cancels out a plus.
Like you're missing electrons.
And a negative charge. Does that make sense? So if you got neutral on the left side, you need to have neutral on the right. And if you see a plus charge, you must have a negative charge to cancel it out. And so the nuts and bolts of NADH has nothing to do with the nicotinamide or the adenine or the dinucleotide or really the hydrogen. It's just all about it turning into an H minus. So this is the biological equivalent of LAD. Or sorry, LDA. Yeah, LAH. LAH is how we make H minus in a pot. Right? This is what we did all day today is LAH. It's the equivalent of having an H minus. In our bodies, NADH does the exact same thing. It's the biological equivalent of H minus. So we don't actually shoot H minuses out into solution. What we do is NAD plus scoops them up and makes NADH. And that's where we get energy out of glycolysis. We actually make NADH. NADH is just like lithium aluminum hydride, except it's in our bodies and it's reversible. So we can use it, we can charge it, we can decharge it, it's fantastic. So I know you guys are signing up or at least meeting your advisors for classes. For biology majors, it's not a requirement to have biochemistry, but I would highly recommend that you guys think about or talk to your advisors about signing up for biochemistry. It's become a much bigger part of the MCAT for pre-med students, the PCAT for pre-pharmacy students. But for any biology major, or I was a biochemistry major, but I loved chemistry, but it just really let me integrate for the first time and see how these things get together and why they matter. And I would say that if you want to be able to apply your organic and have it really mean anything to your future, biochemistry really shows you why all of this organic matters to biological systems. So that's my advertisement for the day, but I recommend biochem to all of you. If there are no more questions, I hope you guys have a great day. I know this was really fast. None of that is quiz stuff, but start thinking about how NADH, whenever you see it in class, no, it's just like LAH. It's how we just biologically make H-. So thanks, and I will talk to you guys all hopefully in class on Friday or in lab next week or sometime next week. Thank you.